So we'll go through some problems for chi-squared tests for independence and for homogeneity, and we'll also do some practice of some older topics. For a project, a student randomly picks 100 fellow AP statistics students to survey on whether each has a PC or Apple at home. All of the students in the school have a home computer, and what score, 1, 2, 3, 4, 5, each expects to receive on the AP exam. A chi-squared test of independence results in a test statistic of 8. How many degrees of freedom are there? So what I'm going to do is I'm going to add a table, and it shows scores 1. Here, let me go ahead and get my pointer. It shows the scores for 1, 2, 3, 4, and 5. So there are 5 rows, and then there are 2 columns, one for PC and one for Apple. So what we'll do is to figure out the degrees of freedom on these tables, you basically cross out one row and one column. So there's one row, there's one column. How many cells are left? 4. So the degrees of freedom is 4. Now, the other way you can do it is you can just say the number of rows minus 1. So 5 minus 1 is 4. And the number of columns minus 1. 2 minus 1 is 1. And 4 times 1 is 4. Gives you the same answer. Number 2, a random sample of 100 former student athletes are picked from each of the 16 colleges that are members of the Big East Conference. Students are surveyed about whether they feel they received a quality education while participating in varsity athletics. A 2 by 16 table of counts is generated. Which of the following is the most appropriate test to determine whether there is a difference among these schools as to the student-athlete perception of having received a quality education? So they said difference among these schools. So they're trying to see if they're different or if they're homogeneous, which means it's a chi-square test of homogeneity. Number 3, a food biologist surveys people at an ice cream parlor, noting their taste preferences and cross-classifying against the presence or absence of a particular marker in a saliva swab test. So relationships means we're testing independence. We're going to conduct a chi-square test for independence. So I'll need some space. And to conduct it, first of all, we have our null hypothesis and alternate. That is that the marker and taste preference are independent. And then the alternate is, oh, they're not independent. There's a relationship. For conditions, we have to check random. Now, in this case, they're just having us do it, but I'm checking conditions just so you can see some extra examples of checking conditions. In this case, she did not say that her sample was random, so we have to assume her sample is representative. All right? 10% condition. We assume 109, that's the total when I add those all up, is less than 10% of all people visiting the parlor. And then calculate expected values and make sure all are at least 5. So we have to do some work for this one. So what you do is you total your rows and you total your columns. Okay. Row 1, we have 44 vanilla. So we would expect this percentage, 44 out of 109, so that's the 0.4037, to have the presence and to have the absence. So 0.4037 times 71 is 28.66. So that's our expected presence right there. I'll round it. And 0.4037 times 38, which is the total down here, is 15.34. Now I'm going to take the 22 over 109. So that's 0.2018. And when I multiply it by 71 and 38, I get 14.3 and 7.7. Then finally, I have 43 out of 109, which is 0.3945. And I'm going to multiply that by 71 and 38, and I get 28 and 15. Well, all expected counts are at least 5, so all my conditions are met. Now, on to the math. So the chi-squared test statistic, you're probably expected to show that you can use this formula. It's on the math chart. So you just need to copy it in. So once you have all these values, you're all set. So chi-squared is your observed, 32, minus 28.7, your expected. Then you square that, and you divide it by your expected value. And you do it for every cell all the way till the end. And I got 2.852, all right? Then if I'm doing this by hand, and you need to know how to do a test statistic. So if I tell you chi-squared is 2.852, and you know the degrees of freedom, which in this case we cross off one column, one row, that leaves us 2 cells. We have 2 degrees of freedom. So we can just basically run that through the calculator. Chi-squared CDF, our lower, we always go above 2.852 to infinity with degrees of freedom of 2. So to find the p-value, we're going to hit second distribution, and we're going to go to the chi-squared CDF, which is 8 down there. Our lower is our test statistic of 2.852. Our upper is always infinity. So I'm going to do as close as we can get to infinity on a calculator, which is 1 times 10 to the 99th. We have 2 degrees of freedom, and you get a p-value of 0.240. So now we have our p-value 0.240, and because our p-value is greater than our alpha 0.05, we fail to reject H0, which means we do not have sufficient evidence for the alternate hypothesis that there is a relationship between the presence of the marker and the flavor preference of ice cream. So going back to our choices now, we have our p-value, and you can see they ask us at different significance levels. Well, 0.24 is greater than both the 10% significance level that they reference, and it's greater than the 5% significance level for sure. So at both of those values, we are going to say we fail to reject. So we have insufficient evidence at either one of those, and saying that we have insufficient evidence at 10% is the same as doing it at 5%, because if it's over 10%, it's definitely over 5%. And now for the much shorter way to do this, you can actually do stat and test. Now we are doing, it's not going to really ask the difference between independence and homogeneity. So it would be C, so it's chi-squared test, you see dot, dot, dot. It's for independence or homogeneity, it's the same thing. Now you'll notice here, it asks for 2 matrices. So I actually need to get out of here. Mode clear is the easiest way for me to do it. And I need to actually edit the matrices. So you can see matrix is down here. So I'm going to hit second and this x to the -1 button. And I want to go to edit a matrix. So I'll hit enter. And our matrix, we have 3 rows and 2 columns. And I'll just put in all of my values in 32, 12, 15. Oops, pretend that's 15. Then we have 7, 24, 19. And my matrix is set. And I'm done. So now I'm going to go ahead and hit stat, test, and go back to that chi-square test. Remember, goodness of fit is for a list of data and a list of expected values. Here we're working with matrices. The nice part is you don't have to set up B. It's going to actually calculate that for you. So that's a super fun thing. And there you can see there's my chi-square test statistic of 2.85. There's my p-value of 0.24. And then let's go look at our expected counts. So we can go, if you hit edit, that's probably the easiest way to see it. Go ahead and hit enter. And then you can see the expected counts right there. So the correct answer is still E. And now for the whoops. All right, so that's it. Number 4. A new fertilizer has been developed by the graduate students in the plant sciences department at your school to increase tomato yield. They decide to test the fertilizer by measuring the number of tomatoes produced by 8 plants, applying fertilizer, waiting 2 weeks, and measuring the number of tomatoes produced by the 4 plants again. The data they obtain are provided below. Assuming all conditions for inference are met, do the data provide convincing statistical evidence that the mean difference in tomato yields is greater when using the new fertilizer? So this is paired data. We have two numbers that naturally go together. For plant 1, the tomatoes before, 3, and 5 after, those go together. So we create a difference, and it's an increase of 2. So you can see like tomato 6 is very plentiful. It has 6 tomatoes before and 9 tomatoes after. And so you can kind of see more easily if we have a significant difference. So it does say assuming all conditions are met. So we'll go ahead and run this using the calculator. So we're going to go ahead, and again, I'm not running all conditions for this where it says assume conditions are met. So I want to do a paired t-test, and you're going, wow, where's the paired t-test? Well, technically it's just a t-test right here. So let's go ahead and look. So what I need to do is input either data or stats, and I can put that in list 1. So I'm going to go back and put my data in, and so I'll hit stat edit, and we'll just type in the numbers here, 2, 4, -1. Oops, it doesn't like, I have to hit the -1 button here. Oops, doesn't matter. Stat edit, go back here, -1, -2, -1, 3, and 1. So now I have my data entered. 7, let's see, I should have 8 data points. Let me double check. 2, I'm missing a 4. I can add it in here at the end. It's not a big deal. All right, so we have 2, then 4, -1, -2, -1, 3, 4, 1. And again, that was the 4 that I left out. So hit stat and then test. All right, we're going to do a t-test. And we have data. Now our hypothesized mean is 0 because we wonder if before or after applying fertilizer that we would have a difference in the average value of tomatoes. So we leave list 1 has our actual data, frequency is 0. Now what is our alternate hypothesis? We believe that there should be an increase in tomatoes, so the difference should be greater than 0. So we hit enter there, and then come down and hit calculate. And voila, there's my t-value. It's 1.488. We have a p-value of 0.09. So with the test statistic of 1.488 and a p-value of 0.090, it's a pretty high p-value. So there is evidence of significance at the 10% level, but not at the 5% level. Number 5, suppose 56% of 8 to 12-year-old students expect to have a great life. In a simple random sample of 125 8 to 12-year-old students, what is the probability that between 50 and 60% will say they expect to have a great life? So basically they told us P is 0.56, N is 125, and we're wondering the probability on our sample of getting between 0.5 and 0.6. So I'm using the sampling distribution, which is on your math chart, and I know that P is 0.56, and then I can substitute in here and say 0.56 times 1 minus 0.56 divided by my sample size, which is 125, and I get my standard deviation. Then I can go ahead and calculate the probability using normal CDF. All right, so we're going to find the probability that it's between 0.5 and 0.6 using the normal distribution, so that's normal CDF. And our lower is 0.5, our upper is 0.6, our mean is 0.56, our standard deviation is 0.0444. And always try and add a few decimals. It doesn't hurt to be extra precise when you're putting these calculations in. And you can see we get a p-value of 0.728, really. And that basically matches our answer of choice D. Number 6. Given these parallel box plots, which of the following is true? Well, for A, it says all three distributions have the same range. Well, range does seem to be the same for all three distributions, so that part's true. But let's check the others. Now we're looking at IQR. Well, the IQRs don't look the same, all right? So B is false. All three medians are between 9 and 13. Well, the bottom distribution, let me go ahead and highlight that for you. The bottom distribution, oh, I thought I got it. Right here, you can see that the median's actually closer to 8, so that is false. And then the top distribution seems skewed to the left, but it's impossible to tell shape from a box plot. So D and E are false. So you really can't tell skew. You have kind of an idea, but you can't really see the shape, so it's a little misleading. So the only one that's true is A. Number 7. Which of the following is a true statement about blocking? Blocking is to experimental design as stratification is to sampling design. That is true. By controlling certain variables, blocking can make conclusions more specific. Oh my goodness, that is true. I must be in trouble because it said, which of the following is true? The paired match pairs comparison design is a special case of blocking. Well, that one's true. Blocking is a useful procedure when there are certain attributes not under study which may affect outcomes. Yeah, so you can try and homogenize your groups, make it easier to see differences. So actually, all of the above are true statements about blocking. Number 8. When leaving for school on an overcast morning, you make a judgment on the null hypothesis. The weather will remain dry. What would the results be of a type 1 and type 2 errors? So our null and our alternate is the null is that it's dry, and the alternate, it's not going to be dry. So type 1 error is when the first one is true. It's actually dry, but you think it's not going to be dry. So if it is really a dry day, but you think it will rain, you carry an unnecessary umbrella. All right, so that's type 1. Type 2, the alternate is true. It's not dry, but you think it's going to be dry. So it's really not a dry day, but you think it will be dry. It rains and you get drenched because you didn't bring an umbrella. Choice B has the answer. Number 9. At the right is the computer output for a regression analysis involving starting salary in thousands of dollars and college GPA. What is the equation for the least squares regression line? So this line right here is always the slope, and it tells you what your x is. Your x is GPA. And the slope is 11.824 or 11.82. So we can pretty much start narrowing down our options here. Then the constant is the y-intercept, all right? And it is negative 0.734. So you can see that our equation is salary equals negative 0.734 plus our slope, 11.82, times our x, which is GPA. The answer is B. Number 10. Suppose a regression line for a set of data, y hat or y predicted, equals 3x plus b, passes through the point 2,5. If x bar and y bar are the sample means of the x and y values respectively, then y predicted, or really should say y bar is what it's asking for. All right, so I guess I have a slight typo on that. So it's passing through the point 2,5. So I'm going to substitute that in the equation to solve for b, right? So here's the 2 and there's the 5. So I get b is negative 1. So that's my y-intercept, all right? Since the regression line always goes through the point x bar, y bar, we can substitute this into the equation, right? So we're going to take y bar and x bar, put it in, and you can see that matches choice E. Number 11. A study of department chairperson ratings and student ratings of the performance of high school stats teachers reports a correlation of R equals 1.15 between the two ratings. From this information, we can conclude that, well, first of all, I'm getting a big red flag because correlation can take any value from negative 1 to 1, but correlation can't be greater than 1, so there must be a mistake in the arithmetic. Number 12. Suppose that in a certain part of the world, in any 50-year period, the probability of a major plague is 0.39, the probability of a major famine is 0.52, and the probability of both is 0.15. What is the probability of famine given that there is a plague. So we're going to go look in our math chart, and we're going to use this right one right here. That's the equation we need because that's the given sign. So the probability of famine given plague is the probability of famine and plague divided by the probability of plague. Well, they told us probability of famine and plague is 0.15, and then the probability of a plague is 0.39, so we get 0.385, which is answer B. Number 13, suppose we have a random variable x where for the values k equals 0 through 10, the associated probabilities are this. What is the mean of x? Well, hopefully you recognize this on the math chart. It's a binomial distribution. And we can see that n is 10, and p is 0.37, and x is k. All right? Now we're trying to find the mean. Well, guess what? That's right on the right of that whole thing. That's the formula for the mean. And so we just substitute in 10 for n and 0.37 for p, and we get 3.7. Number 14. This one's a little trickier than the average one, so here we go. Boxes of 50 donut holes weigh an average of 16 ounces with a standard deviation of 0.245 ounces. If the empty boxes alone weigh an average of 1 ounce with a standard deviation of 0.2 ounces, what are the mean and standard deviation of donut hole weights? So first of all, this is a combination where we have to look at the weight of the box plus each of the 50 donut holes. So my total weight is the box plus donut hole 1 plus donut hole 2, etc., all the way to donut hole 50. If I'm going to do expected value, I can do expected value for the box plus donut hole 1 plus donut hole 2, etc. Well, those donut holes should have the same expected value, which is just for a donut, right, for one donut hole. And what I can do is substitute in what I know. Expected total weight is 16. The expected weight for the box is 1. So 15 is equal to 50 times the expected weight of one donut hole divided by 50, and we get 0.3. Now we need to calculate standard deviation. So since this is a combination, we must work in variance. So the variance of the total equals the variance of the box plus the variance for donut hole 1 all the way through donut hole 50. Well, luckily those 50 donut holes have the same variance. So now I can solve this and start substituting in what I know. Notice that I squared the 0.245. Why? Because this is standard deviation. It's not variance. And to get variance, you have to square the standard deviation. Then I subtract that from both sides and then divide by 50. And I should get a value of 0.000405. But that's not the answer. And you're like, wait, there's nothing like that there. Well, that's the variance. To get the standard deviation, I have to square root that number, which gives me 0.020. So the correct answer is B. Now, if all the values of a data set are the same, all of the following must equal 0 except for which one? Well, let's just go ahead and make up a set of data to check. So I did a bunch of 8s into Staplet just for the fun of it. And you can see the standard deviation is 0. The mean is 8. I chose 8 as my number. The variance is standard deviation squared, which is 0. The range, max minus min, is 0. And IQR, which is Q3 minus Q1, that would be 8 minus 8, is also 0. So the answer is A. Mean is the only one that